Section 3 of Chapter 1 focuses on average rate of change. It's an incredibly important idea for the derivative, another very fundamental operation in calculus. So far we've talked a lot about limits, which are important, but the derivative is even more important. Very, very fundamental to calculus, and that's where we're headed. So let's go ahead and talk about average rate of change for a little while, and then we'll circle back to derivatives very soon. So an average rate of change, it's just another way of saying what's the slope, how much is something changing over time. And we'll get into a mathematical formula, but really it's, if you remember the slope formula from algebra, I'll go ahead and just write that on the screen. M is equal to y2 minus y1 over x2 minus x1. This is the idea. It's exactly the same thing. It's just we often use, a function notation to do that. So let's just look at an idea, but I want to describe what's the idea of an average rate of change, and also talk about what we refer to as an instantaneous rate of change. Those things are different, and those describe kind of the difference between like this, which is a slope, an average slope, between what a derivative is, and we'll kind of build up to why a derivative requires a limit to calculate. But the average rate of change, let's say that you drive 160 miles in 2 hours. The question is, well, what is your average speed? What is the average rate of change that you've been moving at over that period of time? Well, you probably remember the formula: distance is equal to rate times time, or rate of speed is equal to distance divided by time. So, R is equal to D divided by T. Or if we just take a ratio, we drove 160 miles, and it took us 2 hours to do that. If we simply divide those, 160 divided by 2, it tells me, well, how many miles did I drive in 1 hour? Now, technically, that doesn't tell me how many miles I drove in. Like, I can kind of imagine, I drove this 160 miles in 2 hours. If you just cut it in half, we technically would not know, were we going the same speed the whole time? That's why we refer to it as an average rate of change, because we don't know that we were going 80 miles per hour the whole trip. But if we were going 80 miles per hour the whole trip, or, again, we often just refer to that as MPH, but it's just a simplified value of the ratio of those units. I lost my train of thought. But yeah, getting back to average rate of change here, it's an average, because I might have been going 70 miles per hour for the first half and then 90 miles per hour for the second half. And the question is, well, do those actually add up? Yeah, they do, but it would take a little bit more thinking. And, it's like an average value. I might have been going a little faster or a little slower, but what I do know for certain is I probably am speeding, and I should watch out for the cops if I've been going 80 miles per hour the whole time. And yeah, so what is instantaneous rate of change, and what is that? And so in the example, I say, well, as you get on the freeway, you floor it, you try to accelerate to speed up so that you are not, slowing other people down or creating a dangerous situation, because you're not going to be going 80 miles per hour when you first get on the freeway. So it says, somewhere as you accelerate, you notice the speedometer reads 75 miles per hour. So you can see the speedometer in your car. It's either increasing or decreasing. You might have the little dial, I forget what you call it. Or my car has a digital speedometer rather than analog. So I can actually see precisely the speed at a particular point in time. Now, those things aren't always accurate, and they're really rounding off your speed, because your speed isn't going to be exactly 75 miles per hour. It might be 74.9 or whatever, but it gives us, a rounded whole number approximation to our current speed. But what I mean by instantaneous rate of change, it tells us what is our speed at a particular point in time. Like if we were looking at a graph of our speed in our car, let's just say this is time over 2 hours, and this is our speed. And let's just say 80 miles per hour, that was our average. As we're getting on the freeway, maybe we were going 40 miles per hour, and then we accelerate to go to 75 miles per hour. And then let's say we drive 75 miles per hour for a little while, and then we get impatient, so we speed up to 90 miles per hour. I'm not saying you should do this, but we're just making up an example and whatever. And then, towards the end, we slow down a little bit because we're texting or something else that I also don't suggest that you do while you're driving. Anyways, you catch my drift. Basically, it's like at one point in time, we say that we have an instantaneous velocity or instantaneous rate of change of 75. And over a period of time, we might have a constant, but that will change. And in the real world, things do change. When we're looking at a derivative, we're often trying to figure out what is the speed at a particular point. But in order to figure out this, it's important to consider what is my average, and basically look at it over a period of time. Like if I look at it over the entire period of time, I could tell my average is 80 miles per hour, and there's various ways of doing this. And actually you can use calculus to take a complicated function and figure out its average, something that you could not do without calculus. And anyways, we're going to start with the idea of average rate of change and work back to the idea of instantaneous rate of change later.